Hello everyone, good morning. This is Bhavgna from Institute of Aeronautical Engineering IARE. Today I am here to explain a concept video of applied physics for AAT2 and my topic is photoelectric effect. My roll number is 24951 A0559 and I'm from the section A of CSE branch. Now let us dive into the introduction without any further delay. The photoelectric effect is a fundamental phenomenon in physics that revolutionized our understanding of light and its interaction with matter. First observed by Heinrich Hertz in 1887 and later explained by Albert Einstein in 1905. The photoelectric effect refers to the emission of electrons from a material, typically a metal. When it is exposed to light of a certain frequency or higher, this discovery challenged the classical wave theory of light, which suggested that the energy of light depends on solely on its intensity. Instead, experiments showed that no electron were emitted if the light frequency was below a specific threshold, regardless of intensity, and the energy of emitted electrons increased within the frequency of the incident light. This puzzling behavior could only be explained by the idea that light consists of discrete particles of energy known as photons, as proposed by Einstein. The photoelectric effect not only provided compelling evidence for the practical behavior of light, but also played a key role in the development of quantum mechanism, earning Einstein the Nobel Prize in Physics in 1921. Let us look at the Let us have a look at the experimental setup now. The basic experimental arrangement includes a metal surface that serves as the emitter, which is photoelectric material, a light source to shine light of varying frequencies and intensities onto the metal surface, a vacuum chamber to prevent interference from air molecules, a, a collector to detect the ejected electrons, an ammeter to measure the photocurrent caused by ejected electrons, a variable stopping potential to study the kinetic energy of electrons. Now we have the diagram here. There is a light falling on the metal surface and the electrons are being ejected. There is an ammeter, battery, and a vacuum chamber connected to it, and we also have a detector in here. Now let us know about threshold energy. Electrons are emitted only if the frequency of light exceeds material specific threshold frequency. Light below this frequency, regardless of its intensity, do not eject electrons. Instantaneous emission. Electrons are ejected almost immediately after the light strikes the surface, with no measurable time lag, even at very low light intensities. Effect of light intensity. If the frequency of light is above the threshold, increasing the light intensity increases the number of emitted electrons and hence the photocurrent, but it does not affect the kinetic energy of individual electron. Kinetic energy of electrons. The kinetic energy of the ejected electron depends on the frequency of light and not its intensity. It is given by K equal to HV uh, minus phi KE. H is Planck's constant, which is 6.626 into 10 to the power minus 24J. V is the frequency of the incident light. Uh, Phi is the work function of the material, that is the minimum energy required to eject an electron. Now let us look at the Einstein's explanation in 1905. In 1905, Albert Einstein provided a quantum explanation for the photoelectric effect based on the concept of photons, like quanta. Light consists of photons, each with energy E equal to h mu by E. When a photon strikes the metal surface, its energy is transferred to a single electron. If the photon energy is greater than the work function, the electron absorbs the excess energy as kinetic energy. Einstein's equation Ke max equal to h mu minus psi Ke, therefore won him the Nobel Prize in Physics in 1921 and validated the practical nature of light. Now, as we can see here, incoming radiation falls on the metal surface, and the electrons will get knocked out after the energy is fallen over metal surface. Now, let us know about the applications of photoelectric effect. So, the first one is solar cells. Convert sunlight into electricity using a semiconductor, photodetectors and sensors. They are also used in cameras, automatic doors, and light sensitive alarms. Study of atomic and material properties. Helps analyze surface properties of material and understands electron dynamics. Vacuum phototubes used in scientific instruments for precise light indication. As we can see here, they are used in exposure meter, solar panel, and camera light meter. Let us get to know about the significance of the photoelectric effect. Classical theory inadequacy. Classical wave theory could not explain the threshold frequency and the instantaneous nature of electron emission. It predicted that the increasing the intensity should increase the energy of electrons, which was not observed. B. Birth of quantum mechanics. The photoelectric effect validated the quantum theory of light and paved the way for modern quantum mechanics. Dual nature of light demonstrated the particle-like behavior of light, complementing its wave-like properties. Now, on the y-axis we have photoelectric current, and on the x-axis we have collector plane potential, and the graph goes like this with the different type of currents. Okay, now the experimental verification of photoelectric effect. Millikan's experiment verified Einstein's photoelectric equation by measuring the stopping potential and confirming the linear relationship between maximum kinetic energy. Photon energy measurement. Modern experiments use monochromatic light sources and advanced detectors to study the photoelectric effect in detail. Millikan's oil drop experiment goes like there are several thousand volts of current is passing by this, and we have a battery over here. There is a uniform electric field passing down the oil like cover, and we have a cover over here. We have sprayed the oil spray here, and we are looking at the uniform electric field through a microscope. Now this is the wavelength and the color theory of photoelectric effect. Anything which is yeah, this is the color theory. Now let us dive into the conclusion. The photoelectric effect demonstrated by Albert Einstein in 1905 plays a crucial role in the development of quantum mechanics. It shows that light can be thought of any being made up of discrete packets of energy called photons or bundles. When light of a sufficiently high frequency strikes a metal surface, it ejects electrons from the metal. This phenomenon cannot be explained by classical wave theory, which predicted that the energy of electrons should depend on the intensity of light. However, experiments showed that the energy of emitted electron depends only on the frequency of light and not on its intensity. Einstein explanations Einstein's explanation, building on Max Planck's work on quantization of energy, proposed that each photon has energy potential to its frequency. If the photon has enough energy to overcome the work function of the metal, it ejects an electron. This discovery led to the realization that light behaves as both a particle and a wave, marking a pivotal moment in the understanding of the dual nature of matter and energy and laying the foundation for the development of quantum theory. Thank you.